Far from the sun, in the cold outer reaches of the solar system, a moon orbits Saturn wrapped in an orange atmosphere so thick that the surface remains hidden from ordinary view. When radar finally pierced that obscuring haze and revealed what lay beneath, the images showed something remarkable. Channels cutting across the landscape in familiar branching patterns. These were rivers, real flowing rivers, following gravity downhill, just as rivers do on Earth, except the liquid filling them is not water. On Titan, Saturn's largest moon, the rivers flow with methane and ethane, liquid hydrocarbons that exist as gases in the warmth of our own world, here transformed into flowing streams by cold beyond easy comprehension. The temperature at Titan's surface remains steady at roughly -179 degrees Celsius, cold enough to freeze water into stone and transform air itself into liquid. At these temperatures, methane behaves the way water behaves on Earth, existing as a liquid that can pool and flow and evaporate and rain. The rivers we see in radar images are real channels carved by real flowing liquid over what may be millions of years of slow erosion. The liquid moves downhill, following the same physical laws that govern rivers everywhere, responding to gravity and topography in ways that create patterns we recognize immediately, despite the alien chemistry. You are listening to the Drowsy Astronaut, and tonight we explore the rivers of Titan, following channels of liquid methane as they wind across a frozen landscape beneath an orange sky. There is no rush in what follows, no test to pass, nothing you need to remember when morning comes. We will simply spend time together, learning about these remarkable features, staying with them as long as we need to understand what flows there. If you enjoy this gentle journey through the outer solar system, consider sharing where you are listening from in the comments, and perhaps a like or subscription if these explorations help you rest. The rivers appear dark in the radar images that revealed them, darker than the surrounding terrain, which tells us they contain liquid rather than solid material. Radar bounces differently from liquid surfaces than from solid ground, allowing scientists to distinguish channels of flowing methane from the land around them. The channels snake across the landscape, branching and merging in dendritic patterns, tree-like networks where smaller tributaries join together to form larger flows. These patterns are universal wherever gravity pulls liquid across sloping ground, whether the liquid is water on Earth or liquid methane on a moon nearly 1 billion miles from the sun. Some of these river systems stretch for hundreds of kilometers across Titan's surface, beginning in highland regions and descending toward the lowland areas near the poles. The longest identified channels exceed 400 kilometers in length, winding through terrain and cutting valleys that can be tens of meters deep. The rivers vary in width, from perhaps a few hundred meters across for smaller channels to several kilometers wide for the largest flows. These are substantial features, comparable in scale to rivers we know on Earth, carved by processes that have operated for geological spans of time. The liquid flowing in these channels moves slowly compared to swift mountain streams on Earth, its motion governed by Titan's low gravity and the physical properties of methane. Gravity at Titan's surface is only about 14% of Earth's gravity, which means water would weigh 7 times less there than here. Liquid methane already weighs about half what water weighs, and under Titan's weak gravity, it becomes lighter still. flowing with less force than water rivers, but flowing nonetheless. The low gravity also means steeper riverbanks can remain stable, allowing channels to cut deeper than equivalent rivers might on Earth. The viscosity of liquid methane, how easily it flows, is lower than water's viscosity, meaning methane is thinner and moves more freely. A river of liquid methane flows about as easily as gasoline flows on Earth, slipping smoothly through its channel with less internal friction than water experiences. This low viscosity, combined with the low gravity, creates flow characteristics different from Earth rivers, with currents and eddies that follow familiar physics, but in slightly altered forms. The fundamental behavior remains the same: liquid responding to gravity and channel shape. But the details shift in ways that would be visible if we could watch the flow directly. At the riverbanks, clear boundaries exist between the liquid methane in the channel and the solid ground beside it, edges where one phase of matter meets another in the cold twilight. The banks appear lighter in radar images, suggesting they are made of solid material, likely water ice as hard as granite at these temperatures, or perhaps solid organic compounds deposited over time. The channels have carved these banks through erosion, the flowing liquid wearing away at the solid surfaces over countless years, deepening and widening the valleys through which the methane moves. This erosion proceeds slowly under Titan's gentle gravity, but geological time allows even slow processes to carve substantial features. Where rivers meet, confluences form just as they do on Earth, multiple channels joining to create larger flows downstream. The tributaries approach the main channel at angles determined by the terrain, merging where topography directs them, creating the branching networks visible from orbit. Some confluences show what appear to be depositional features, places where material carried by the rivers settles out when flow slows at the junction. These deposits suggest the methane carries suspended particles with it, perhaps grains of ice or organic compounds eroded from the landscape upstream. The rivers lead eventually toward destinations in the polar regions, where vast lakes collect the flowing methane into reservoirs that dwarf any river channel. The northern polar region of Titan particularly shows extensive channel networks draining toward the seas. We will explore in detail as our journey continues. For now, what matters is understanding that these rivers are not isolated features, but parts of an interconnected system where liquid flows from highlands to lowlands, gathering and joining on its journey toward those distant seas. The rivers serve as the connecting pathways in a cycle that moves methane across the moon's surface. In some regions, particularly near the equator, channels exist that appear dry in current observations, valleys carved by flowing liquid but containing no liquid now. These dry riverbeds suggest that rivers do not flow everywhere all the time on Titan, that some channels carry liquid only seasonally or during particular climate conditions. The presence of dry channels tells us about changes over time, about periods when methane flowed where it does not flow now. Whether these channels will fill again depends on Titan's complex weather patterns and the seasonal distribution of methane across the moon. The actual appearance of the liquid methane in these rivers, could we see it directly, would be clear or perhaps slightly tinted rather than the murky brown of many Earth rivers. Methane and ethane are both clear liquids when pure, transparent, like water or alcohol, though the presence of dissolved materials might add color. The riverbed beneath the flowing liquid might be visible through the clear methane, the substrate of ice and organics showing through the shallow flow. The surface of the liquid would reflect light, though under Titan's dim orange sky, the reflections would be muted and tinted by the atmosphere's pervasive haze. The depth of these rivers remains uncertain. Radar can tell us where liquid exists, but provides limited information about how deep it flows. Some channels may be quite shallow, perhaps only meters deep, with the liquid flowing in a thin layer across the channel floor. Other rivers might be deeper, cutting through the landscape to create channels tens of meters from surface to bed. The flow rate depends on depth, slope, and channel width, and these variables interact to determine how much liquid moves through each system. The total volume of methane flowing through Titan's river networks at any given time is modest compared to the amount stored in the polar lakes and seas. The speed of flow in these rivers is probably slow by Earth standards, measured in centimeters or perhaps tens of centimeters per second rather than meters per second. The combination of low gravity, gentle slopes in many regions, and modest liquid volumes creates leisurely flows that would appear almost still if viewed briefly. Yet even slow flows transport material and erode channels when given geological time to work. A river flowing at 10 centimeters per second still moves 3.5 kilometers in a day, carrying whatever it transports steadily toward its destination over days and weeks and years. Seasonal variations likely affect these rivers as Titan's long seasons progress, though the full cycle takes nearly 30 Earth years to complete. During Titan's northern summer, when the North Pole receives more sunlight, evaporation from the northern seas feeds moisture into the atmosphere that later falls as rain over northern latitudes. This rain swells the rivers that drain into those northern seas, increasing their flow in a feedback cycle that appears to operate over years. The southern hemisphere, which receives less rain overall, has fewer large rivers and less developed channel networks, suggesting the distribution of flowing liquid varies considerably across the Moon. The formation of these river channels happened over very long timescales, carved gradually through erosion as methane flowed repeatedly through the same paths. Unlike some features on planetary surfaces that form suddenly through impacts or volcanic events, river channels require sustained flow over extended periods to cut through solid material and establish their courses. The channels we see today represent perhaps millions of years of flow, though the rates of erosion at Titan's cold temperatures and low gravity are difficult to estimate precisely. The networks exist because conditions have allowed liquid methane to flow across the surface for geological ages, stable enough to carve permanent features. The braided channels visible in some regions reveal another aspect of how these rivers behave, showing where single channels split into multiple smaller streams that weave around each other. Braiding occurs on Earth, where rivers carry abundant sediment and flow across relatively flat terrain, conditions that may also exist in certain areas on Titan. The braided sections suggest that the rivers carry material with them, depositing it as flow slows or shifts, creating the islands and bars that divide the flow into multiple paths. These depositional features provide evidence of active sediment transport, of the rivers doing real work in shaping the landscape. Delta structures appear where rivers enter the larger lakes, spreading out into multiple distributary channels as flow velocity drops in the standing liquid. These deltas resemble river deltas on Earth, showing the familiar fan-shaped pattern that develops when flowing water, or in this case flowing methane, encounters still water and drops its sediment load. The material transported by the river settles in the quieter environment of the lake margin, building up deposits that extend the land into the liquid. The deltas grow over time, advancing into the lakes as material accumulates, creating new land from transported sediment. The tributaries feeding these rivers range from small channels barely resolvable in radar images to substantial flows several kilometers wide. The smallest tributaries begin in highland regions where slopes are steeper and where rainfall or seepage supplies liquid to the emerging channels. These small channels merge downhill with others, growing through the natural aggregation that creates river systems everywhere. The drainage basin of each major river encompasses the land area that contributes flow to that system. Regions where rain falls or methane seeps from below to eventually join the channel network, leading to the polar seas. The solid material making up the landscape through which these rivers flow consists primarily of water ice, which at Titan's temperatures behaves mechanically like rock does on Earth. Water ice this cold is hard and brittle, strong enough to support mountains and resist erosion for geological time. The rivers must erode this ice slowly, wearing it away through the persistent flow of liquid methane over millions of years. The material eroded from the ice bedrock becomes the sediment the rivers carry, though whether it remains as ice particles or transforms into something else during transport remains uncertain. Organic compounds likely mix with the water ice in Titan's surface materials, complex molecules that have fallen from the atmosphere over billions of years. These organics, tholins and other hydrocarbons, may constitute some of the sediment the rivers transport, carried in suspension or rolling along the channel bottom as the liquid flows. The organic material is solid at Titan's temperatures, behaving as particles rather than dissolving into the methane. Though some degree of solution may occur for certain compounds, the rivers thus serve as transport systems for organic chemistry, moving molecules from one part of Titan's surface to another. The channels themselves provide evidence of Titan's active surface processes, showing that this moon is not a frozen, unchanging world, but rather a place where fluids flow and landscapes evolve. The presence of extensive river networks indicates that the methane cycle has operated for long periods, stable and persistent enough to carve the features we observe. This activity places Titan in a rare category among moons and planets, one of only 2 worlds in the solar system where stable liquid exists at the surface and shapes the terrain through familiar geological processes. Earth is the other world, with its global water cycle and water-carved landscapes, making Titan a distant analogue despite the differences in chemistry and temperature. As these rivers flow across Titan's landscape, they ultimately deliver their liquid to destinations that dwarf them in scale. The lakes and seas that collect methane in vast reservoirs near the poles. The seas are where our exploration continues, following the rivers to their endpoints and discovering the standing bodies of liquid that have no true parallel elsewhere in the solar system, except on Earth. The rivers are the pathways. The seas are the destinations in a hydrocarbon cycle that operates across this remarkable moon. The rivers we have been following all lead eventually toward bodies of liquid that sit in depressions near Titan's north and south poles, collecting the methane and ethane into reservoirs of extraordinary size. These are not puddles or small ponds, but vast seas, the largest of them covering areas greater than some of Earth's largest lakes and containing volumes of liquid measured in thousands of cubic kilometers. The northern polar region particularly holds a concentration of these liquid bodies, clustered together in a landscape dominated by the dark radar signature of standing liquid, bordered by the lighter signature of solid ground. Kraken Mare stretches across roughly 400,000 square kilometers of Titan's northern polar region, making it larger than the Caspian Sea on Earth, and by far the largest known body of liquid on any world besides our own. The sea extends roughly 1,000 kilometers from its southern reaches to its northern extremes, a vast expanse of liquid hydrocarbons sitting in a basin that has collected methane and ethane for uncounted millions of years. From orbit, Kraken Mare appears as an irregular dark shape in radar images, its shoreline complex and indented with bays and peninsulas that suggest a complicated topography beneath the liquid surface. Ligeia Mare sits to the west of Kraken Mare, the second largest of Titan's seas, covering approximately 130,000 square kilometers. This sea has been studied in particular detail by the Cassini spacecraft, which used radar to probe not just the sea's extent, but also its depth in certain locations. The measurements revealed that Ligeia Mare reaches depths of at least 160 meters in some areas, deeper than most lakes on Earth, and comparable to significant Earth seas. The depth indicates that these are not shallow pools, but substantial bodies of liquid with vertical extent as well as horizontal spread. Punga Mare, smaller than the other two major seas but still substantial, completes the trio of large northern liquid bodies. Together, Kraken, Ligeia, and Punga form a system of connected or nearly connected seas that dominate Titan's North Polar landscape. The proximity of these three seas to each other suggests they may share a common geological setting, perhaps filling a region of lower elevation created by ancient processes that shaped Titan's crust. The concentration of large liquid bodies in this region makes the North Polar area unlike anywhere else on the Moon, a landscape defined by the interface between solid land and liquid sea. The southern hemisphere shows a dramatically different pattern, with far fewer and smaller lakes despite the southern polar region presumably being able to collect liquid, just as the north does. The largest southern liquid body is Ontario Lacus, which extends roughly 235 kilometers in its longest dimension, substantial but much smaller than the northern seas. The asymmetry between northern and southern liquid distribution is one of Titan's puzzling features, suggesting that factors beyond simple polar geography influence where liquid accumulates. The asymmetry may relate to differences in topography, with the northern region sitting at lower average elevations that naturally collect draining liquid. The liquid filling these lakes and seas consists primarily of liquid methane with ethane dissolved into it, creating a mixture of light hydrocarbons that remains liquid at Titan's surface temperature. The ratio of methane to ethane likely varies between different lakes and at different depths within the same lake, as the two substances have slightly different properties. Ethane is denser than methane, which might cause stratification within the deeper seas, with ethane concentrating near the bottom, while methane dominates near the surface. The exact composition can only be inferred from remote observations, as no probe has yet sampled the liquid directly from any of Titan's seas. The depth of the seas varies considerably across their extent, with shallow marginal areas around the edges deepening toward the centers of the larger basins. Ligeia Mare's measured depth of 160 meters represents soundings from specific locations, likely near the center of the sea, while areas near the shores are presumably much shallower. The depth profile of a sea depends on the shape of the basin containing it, which in turn depends on the geological processes that created that basin. Whether these basins formed through tectonic processes, through dissolution of surface materials, or through other mechanisms remains an area of active study. The shorelines of these seas show remarkable detail in high-resolution radar images, revealing bays, inlets, and what appear to be river mouths where channels deliver liquid from the surrounding terrain. The complexity of these shorelines rivals the complexity of Earth coastlines, showing that the boundaries between liquid and solid are shaped by similar processes on both worlds. Erosion by waves, deposition of sediments from rivers, and perhaps seasonal variations in liquid level all contribute to the shoreline shapes we observe. The edges, where liquid meets land, are dynamic boundaries rather than static lines. Islands appear within some of the seas, areas of higher ground that rise above the liquid surface to create isolated landmasses surrounded by methane. These islands show the same radar-bright signature as the surrounding shores, indicating they are made of solid material, likely water ice and organic compounds. The presence of islands suggests that the basin topography beneath the liquid is varied, with elevated regions that remain above the liquid level, even when the sea is relatively full. Some features, initially identified as islands in earlier observations, appeared to change or disappear in later imaging, suggesting either changes in liquid level or possibly floating objects. The possibility of floating features in Titan's seas raises intriguing questions about what might exist on or in these liquid bodies. On Earth, ice floats on liquid water, but water ice is denser than liquid methane and would sink rather than float. However, certain forms of frozen methane or nitrogen might be less dense than liquid methane and could potentially float. Solid organic materials might also achieve neutral buoyancy, neither sinking nor floating, but suspended in the liquid. Whether any such materials actually exist in sufficient quantities to create observable floating features remains uncertain. Coastal features around the lakes include what appear to be beaches or erosional platforms at the liquid margins, zones where the interaction between liquid and solid creates particular surface textures. Some shores appear smooth and gradual, while others show steeper boundaries, suggesting cliffs or scarps meeting the liquid directly. The variety of coastal morphologies indicates that different processes operate in different locations, or that the same processes interact with different underlying materials to create varying results. Understanding these coastal features helps reveal how Titan's seas interact with the land around them. The surfaces of the seas are probably calm most of the time, lacking the vigorous wave action that characterizes Earth's oceans. Wind exists on Titan, but generally blows gently, typically only a few meters per second, which would generate only modest waves on a liquid surface. The low gravity also affects wave behavior, creating waves that would be larger in wavelength but lower in height compared to wind of equivalent strength on Earth. An observer at the shore of a Titan sea might see small ripples rather than crashing breakers, the liquid surface moving gently under the influence of the weak winds. Flooded river valleys appear where rivers enter the seas, showing the transition from flowing channel to standing liquid. These valleys extend into the seas as submarine features, channels cut during times when sea level was lower and the rivers flowed across what is now the sea floor. The presence of these flooded valleys indicates that liquid levels have varied over time, with the seas sometimes sitting lower in their basins than they do in current observations. Sea level changes on Titan could result from seasonal transfers of methane between different latitudes, or from longer-term climate variations that redistribute liquid across the Moon's surface. The total volume of liquid in Titan's lakes and seas has been estimated from the known surface areas and the limited depth measurements available, producing figures in the tens of thousands of cubic kilometers. This represents an enormous reservoir of liquid methane and ethane, far exceeding the volume of liquid in rivers or falling as rain at any given moment. The seas serve as storage for the bulk of Titan's surface liquid, with the rivers and rain representing liquid in transit through the hydrocarbon cycle. The stability of these large reservoirs over geological time suggests that they are fundamental features of Titan's surface, present for as long as the current climate regime has persisted. Variations in liquid level within the seas have been detected through repeated observations over the years of Cassini's mission, showing that these are not static bodies, but ones that respond to the cycle of evaporation, rainfall, and river input. Some smaller lakes in the south appeared to change significantly between observations, separated by several years, with a few apparently drying up completely or filling for the first time. These changes demonstrate that Titan's hydrocarbon cycle is active on timescales of years to decades, moving liquid between reservoirs and changing the distribution of surface features. The larger seas show less dramatic change, their vast volumes buffering against rapid fluctuations. The chemistry within the seas likely differs from the chemistry of the atmosphere above, or the solid surface around them, creating distinct environments with their own characteristics. Substances dissolved in the liquid could support different reactions than occur in the atmosphere, and the stable temperature and pressure at depth might preserve compounds that would quickly react away if exposed at the surface. The seas are isolated from direct sunlight below depths of a few tens of meters, creating dark environments where only dissolved or suspended materials exist, without the photochemical processing that dominates the atmosphere. These deep liquid environments represent a regime we have not yet explored directly. The northern seas occupy a region of Titan that receives varying amounts of sunlight over the course of Titan's long year, experiencing the extremes of northern winter when sunlight barely reaches the poles, and northern summer when continuous illumination provides maximum energy. These seasonal variations drive changes in evaporation rates, with summer increasing evaporation and winter reducing it. The interplay between evaporation, precipitation, and river input creates a dynamic balance that determines sea level at any given time. The northern summer has been observed to correlate with increased cloud activity in the region, suggesting enhanced evaporation and rainfall during this season. The three major northern seas, Kraken, Ligeia, and Punga, may be connected by straits or channels that allow liquid to flow between them, creating a unified system rather than isolated basins. Some radar images show what appear to be passages between the seas, narrow connections where liquid could move in response to level differences or wind-driven currents. If connected, the seas might exchange water, or rather, exchange methane, redistributing dissolved substances and homogenizing their compositions over time. The question of connectivity versus isolation affects predictions about how each sea responds to seasonal forcing. The study of Titan's lakes and seas provides a window into processes that operate on only one other world in our solar system. The processes by which liquid pools at the surface, evaporates, rains, and flows in a continuous cycle. These processes shape the landscape, transport materials, and create the diverse surface features that make Titan such a complex world. Above these seas and lakes hangs the thick atmosphere that makes the hydrocarbon cycle possible, an envelope of nitrogen and methane that we will explore next as our journey continues outward from the liquid surface to the orange air above. The liquid methane sitting in Titan's lakes and flowing through its rivers exists beneath a blanket of air thicker and denser than Earth's atmosphere, a substantial envelope of gas that extends hundreds of kilometers above the moon's surface. This atmosphere presses down on the surface with 1.5 times the pressure of Earth's atmosphere at sea level, creating conditions where gases that would be impossibly thin on a smaller moon instead form a heavy, viscous layer. The composition differs dramatically from the air we breathe, primarily nitrogen like Earth's air, but with methane playing the role that water vapor plays in our atmosphere, providing the substance that cycles between gas, liquid, and the occasional solid state. Nitrogen comprises roughly 95% of Titan's atmosphere, making this moon unique among satellites in having an atmosphere dominated by this particular gas. Earth shares this nitrogen dominance, both worlds wrapped in air made mostly of the same molecule, though the similarities end there. On Earth, nitrogen exists alongside substantial oxygen, a product of billions of years of photosynthetic life that transformed our planet's air. On Titan, oxygen is essentially absent, locked into water ice that remains frozen as solid as rock. The nitrogen itself is lighter than the air on Earth, despite Titan's atmosphere being denser overall, a consequence of the cold that compresses everything closer to the surface. Methane makes up most of the remaining 5% of Titan's atmosphere, playing a crucial role despite its minority status. Methane in Titan's atmosphere is what water vapor is in Earth's, the substance that evaporates from surface reservoirs, rises into the air, condenses into clouds, and falls as precipitation. This methane weathers erosion, transports materials, and drives atmospheric dynamics through its phase changes. The amount of methane in the atmosphere is carefully balanced, enough to support cloud formation and rainfall, but not so much that the sky would be opaque to all wavelengths of light. The balance is maintained by the cycle of evaporation, condensation, and precipitation that moves methane continuously between surface and air. The atmosphere's orange color comes from organic molecules suspended in the upper layers, complex compounds that form when sunlight breaks apart methane molecules and the fragments recombine into larger structures. These molecules, called tholins, consist of carbon, hydrogen, and nitrogen, arranged in complex ways that scatter light, preferentially blocking blue wavelengths, while allowing orange and red light through. The result is a pervasive orange haze that obscures the surface from visible light observation and gives Titan its distinctive color when viewed from space. The haze is densest at altitudes above 200 kilometers, but extends throughout the atmosphere to some degree, creating layers of varying opacity. At the surface, beneath all these layers of haze, the air is clearer than the upper atmosphere, but still tinged with orange from the light filtering down through the overlying layers. Visibility at the surface would extend to the horizon in most conditions, allowing a ground-level observer to see across the landscape, despite the haze above. The thickness of the air at this level is noticeable, roughly 4 times denser than the air at sea level on Earth, creating an environment where aerodynamic effects dominate over simple ballistic motion. Objects moving through this thick air would experience significant drag, while objects less dense than the air could potentially float even without active lift. The pressure at the surface, 1.5 times Earth's sea level pressure, means that the air presses against everything with substantial force, though not enough to create difficulties for equipment designed to withstand it. This pressure is high enough that nitrogen remains in gaseous form despite the cold, only approaching condensation at the very coldest temperatures that occur at Titan's surface. Methane sits closer to its condensation point, able to exist as either liquid or gas, depending on small variations in temperature and pressure. The pressure also affects how liquids behave, allowing methane to remain liquid at temperatures where lower pressure would cause it to boil. Temperature throughout the atmosphere varies with altitude, generally decreasing from the surface upward through the lower atmosphere, before reversing in the upper layers, where solar radiation deposits energy directly. At the surface, the temperature holds remarkably steady at -179 degrees Celsius, varying by only a few degrees between different locations and seasons. This uniformity reflects the atmosphere's efficiency at redistributing heat, moving warmth from regions receiving more sunlight toward regions receiving less. The thick air and slow rotation help maintain this temperature stability, preventing the extreme variations between day and night that occur on airless worlds. The sky above Titan's surface appears orange overhead, fading to a brownish hue near the horizon, where the line of sight passes through more atmosphere and therefore more obscuring haze. The sun, when visible through the haze, appears as a dim, diffuse glow rather than a distinct bright disk. Its light scattered by the organic particles throughout the atmosphere. The intensity of sunlight reaching Titan's surface is only about 1% of what reaches Earth's surface, creating perpetual twilight conditions. This dimness is partly due to Titan's distance from the Sun, nearly 10 times farther than Earth, and partly due to the light absorbed and scattered by the thick, hazy atmosphere. Clouds form at various altitudes in Titan's atmosphere, though cloud cover is not constant or global as it is on Venus. Methane clouds develop when temperature and humidity conditions allow methane vapor to condense into liquid droplets or possibly into solid methane particles at higher, colder altitudes. These clouds appear bright in certain infrared wavelengths, allowing them to be tracked from orbit even when invisible in other parts of the spectrum. The clouds tend to form at middle and high latitudes, particularly during the appropriate seasons when conditions favor methane condensation. They shift and evolve over hours and days, creating weather patterns that Cassini observed throughout its long mission. Wind patterns on Titan generally remain gentle compared to Earth's vigorous atmospheric circulation, with surface wind speeds typically measured in single-digit meters per second. The winds flow in response to subtle pressure differences created by uneven solar heating and by the condensation and evaporation of methane at different locations. Near the equator, winds tend to blow from east to west, following the same direction as the atmosphere's overall rotation. At higher latitudes, circulation patterns become more complex, influenced by seasonal changes in sunlight distribution. The weak winds are sufficient to transport particles, shape dunes in equatorial regions, and generate small waves on the surfaces of the northern seas. The slow rotation of Titan, it takes nearly 16 Earth days for the Moon to complete one rotation, affects atmospheric circulation patterns in ways that differ from Earth's much faster rotation. The Coriolis effect, which on Earth strongly influences weather patterns and creates distinct circulation cells at different latitudes, operates much more weakly on Titan due to the slow rotation. This allows air masses to flow more directly between equator and poles without being deflected as strongly into east-west circulation. The atmospheric circulation on Titan is therefore more influenced by simple convection and direct response to heating patterns than by rotation-induced effects. The methane in Titan's atmosphere slowly disappears through photochemical reactions that break the molecules apart when they are struck by solar ultraviolet light. This destruction happens primarily in the upper atmosphere, where UV light penetrates, converting methane into other molecules and gradually depleting the atmospheric reservoir. The rate of methane destruction means that the current atmospheric content should be removed over tens of millions of years, unless something replenishes it. The methane we observe today cannot have been in the atmosphere since Titan's formation billions of years ago, requiring that some source continuously or periodically adds methane to maintain the observed concentrations. The source of methane replacement could be the surface lakes and seas, evaporation returning to the atmosphere what rain removes, creating a closed cycle that maintains balance. However, calculations suggest that this surface reservoir alone may not be sufficient to maintain atmospheric methane over geological time, given the photochemical destruction rate. Another possibility is that methane emerges from Titan's interior, either through volcanic-like processes that bring methane from depth, or through gradual seepage from internal reservoirs. Understanding the methane budget, how much is destroyed, how much is added, and where it comes from, remains an active area of research, with implications for Titan's long-term evolution. The atmospheric layers extend upward from the surface through a troposphere, where temperature decreases with altitude, through a tropopore's boundary, and into a stratosphere where temperature increases with height due to solar heating. The troposphere extends to roughly 40 kilometers altitude, within which most weather and cloud formation occurs. Above this lies the stratosphere, reaching up to several hundred kilometers, where the organic haze forms and photochemistry dominates. The uppermost regions of the atmosphere gradually thin into space, with no sharp boundary, but rather a gradual transition, where atoms and molecules become sparse enough that collisions are rare. Atmospheric chemistry in the upper layers produces dozens of different organic compounds, beyond simple methane and ethane, creating a complex mixture that slowly evolves as sunlight drives reactions forward. Propane, acetylene, hydrogen cyanide, and many other molecules have been detected in Titan's atmosphere, each present in trace amounts, but together representing a diverse chemical environment. These molecules form through chains of reactions starting with methane destruction and proceeding through multiple steps of combination and recombination. Some eventually grow large enough to become the tholins that create the haze, while others remain as gases, contributing to atmospheric composition. The greenhouse effect on Titan, though modest compared to Venus or even Earth, plays a role in determining surface temperature. Methane and other molecules in the atmosphere absorb infrared radiation emitted by the surface, trapping some of the heat that would otherwise escape directly to space. This warming effect raises surface temperature by perhaps 10 to 20 degrees Celsius above what it would be without the atmosphere. The effect is limited by the atmosphere's composition and the low intensity of sunlight available to warm the surface initially. Without the greenhouse warming, methane would freeze at the surface, eliminating the liquid hydrocarbon cycle entirely. The thickness and density of Titan's atmosphere make it an ideal environment for flight, either for lighter-than-air vehicles or for windcraft that generate lift aerodynamically. The low gravity reduces the weight that must be supported, while the dense air provides substantial lift for even modest wing surfaces. A human with appropriately designed wings could potentially achieve flight through muscle power alone under these conditions, something impossible on Earth. This characteristic has influenced plans for future missions, including concepts for aerial vehicles that could explore Titan's surface from the air more efficiently than rovers could move on the ground. This thick, orange, nitrogen-rich atmosphere drives the weather that creates the hydrocarbon cycle, moving methane from lakes to clouds to rain and back to the surface in patterns we will explore next. The cycle connects atmosphere and surface, creating the dynamic system that makes Titan one of the most Earth-like worlds, despite the differences in chemistry and temperature. Understanding how methane moves through this cycle helps explain not just Titan's current state, but also how the Moon has evolved over billions of years. The methane cycle on Titan operates through the same fundamental processes that drive Earth's water cycle, moving a substance from liquid on the surface to vapor in the atmosphere, to liquid falling as precipitation and flowing back to the surface reservoirs. Liquid methane sitting in the northern seas absorbs heat from the environment, though heat on Titan means something different than on Earth. The faint sunlight provides modest energy even at these extreme distances. The methane molecules at the liquid surface occasionally gain enough energy to break free from their neighboring molecules and enter the atmosphere as vapor, evaporation proceeding continuously, but slowly in the cold environment. The rate of evaporation depends on temperature, with warmer conditions increasing the rate at which molecules escape from the liquid surface. On Titan, temperature variations are small, but even a difference of a few degrees between seasons or locations affects how quickly methane evaporates. Wind also influences evaporation rate, with moving air carrying away the methane vapor that accumulates just above the liquid surface and allowing fresh air to contact the liquid. The combination of temperature and wind determines how much methane enters the atmosphere from the surface at any given time and place. During northern summer, when the northern seas receive more sunlight and temperatures rise slightly, evaporation increases compared to winter. Once in the atmosphere, methane vapor becomes part of the air, mixing with nitrogen and rising through convection and atmospheric circulation. The vapor moves with air masses, transported by winds from regions where evaporation is strong, toward regions where conditions favor condensation. As vapor-containing air rises or moves toward colder regions, the temperature drops and methane's capacity to remain as vapor decreases. When the air becomes saturated with methane vapor, holding as much as the temperature and pressure allow, any further cooling or addition of vapor causes condensation to begin. Condensation forms liquid methane droplets around tiny particles in the atmosphere, creating clouds visible both from the surface and from orbit. These clouds appear similar in principle to water clouds on Earth, though the details differ due to methane's properties and Titan's atmospheric conditions. The droplets grow as more vapor condenses onto them, increasing in size until they become heavy enough to fall despite the low gravity. The thick atmosphere slows their descent, allowing droplets to fall gently compared to rain on Earth. Individual raindrops of methane on Titan may grow larger than Earth raindrops, reaching perhaps 5 millimeters in diameter before falling becomes inevitable. Methane rain falls from clouds when conditions are right, though rain appears to be less frequent on Titan than on Earth. Observations suggest that rainfall is episodic rather than constant, with periods of rain separated by longer dry intervals. The rain falls more frequently at higher latitudes, particularly in the northern polar region, during northern summer when evaporation from the northern seas is strongest. Equatorial regions receive less rain, evidenced by the dry riverbeds that show past flow but contain no liquid now. The seasonal and latitudinal distribution of rainfall creates patterns in surface liquid distribution, with polar lakes persisting while equatorial channels only occasionally fill. When methane rain reaches the surface, it collects in topographic lows, forming puddles and streams that join to create the river networks we explored earlier. The flowing liquid follows gravity downhill, carving channels through the surface materials and transporting particles along its path. The rivers deliver this liquid eventually to the lakes and seas, completing the cycle that began with evaporation. The time required for methane to complete a full cycle, from sea to atmosphere to rain to river and back to sea, varies depending on the path taken. Some methane might evaporate and rain back into the same sea within days, while other molecules might travel for months before returning to a surface reservoir. Seasonal variations drive changes in the cycle's intensity and the locations where different phases dominate. Titan's seasons are long by human standards. Each season lasts about 7.5 Earth years, because Titan orbits Saturn, and Saturn takes nearly 30 Earth years to orbit the Sun. As Saturn moves through its orbit, the tilt of its axis causes first one hemisphere of Titan, and then the other, to receive more direct sunlight. During northern summer, the North Pole is tilted toward the Sun, receiving continuous sunlight at the most extreme latitudes and enhanced sunlight at all northern latitudes. This increased solar input warms the northern region, enhancing evaporation from the northern seas. The increased evaporation during northern summer puts more methane vapor into the atmosphere over the northern polar region, and this vapor forms clouds that produce rain, feeding back into the northern seas and filling the rivers that drain into them. This positive feedback can create periods of enhanced activity in the hydrocarbon cycle, with more evaporation leading to more clouds, leading to more rain, leading to higher lake levels. Observations during Cassini's mission documented this process, watching as the northern summer progressed and cloud activity increased in the northern latitudes. The cycle strengthens during the appropriate season and weakens during winter when temperatures drop and evaporation slows. The southern hemisphere's hydrocarbon cycle is less vigorous than the northern system, though the underlying processes are the same. The southern polar region has fewer and smaller lakes, providing less surface area for evaporation, and therefore less vapor to drive the cycle. Whether this asymmetry results from differences in topography, perhaps the southern region sitting at higher average elevations where liquid drains away more readily, or from other factors remains uncertain. The smaller southern reservoir means that southern summer, when it arrives, might not produce the same level of cycling activity that northern summer does, though observations of a full southern summer have not yet been possible. The energy driving the methane cycle comes primarily from sunlight, the same source that drives Earth's water cycle, though the amount of solar energy available at Titan is far less than at Earth. The Sun, at Titan's distance, delivers only about 1% of the energy per unit area that it provides to Earth, spread across the year and distributed unevenly by latitude and season. Despite this low energy input, it proves sufficient to evaporate methane from the surface, lift vapor into the atmosphere, and drive the circulation that creates clouds and rain. The cycle operates in slow motion compared to Earth's vigorous water cycle, but it operates nonetheless, demonstrating that even modest energy sources can drive planetary processes. The total amount of methane cycling through the atmosphere at any given time is small compared to the amount stored in the surface lakes and seas. The atmosphere contains the equivalent of only a few meters of global liquid methane, while the lakes contain hundreds or thousands of times more. This means the atmospheric reservoir turns over relatively quickly, with methane evaporating from the surface, spending days to weeks in the atmosphere, and returning as rain. The surface reservoirs, in contrast, represent long-term storage, accumulating liquid over geological time and releasing it slowly through evaporation. The relationship between atmospheric and surface methane determines how quickly the cycle responds to changes and how stable the system is over time. Methane in the atmosphere is gradually destroyed by photochemical reactions, breaking down into other compounds that do not participate in the cycle in the same way. This loss must be balanced by fresh methane entering the atmosphere, either from surface evaporation or from internal sources we will explore later. If the destruction exceeded replenishment, atmospheric methane would decrease over time, weakening the cycle and potentially ending it entirely. The fact that substantial atmospheric methane exists today, billions of years after Titan's formation, indicates that replenishment has matched or exceeded destruction, maintaining the cycle across geological time. The methane cycle shapes Titan's surface in ways that few other processes can at these cold temperatures. Erosion by flowing liquid carves channels, deposits sediments in new locations, and slowly modifies the landscape over millions of years. Rainfall dissolves or mechanically breaks down surface materials, transporting them to new locations where they settle and accumulate. The cycle also transports heat, with evaporation cooling the surface where it occurs, and condensation warming the atmosphere where clouds form. These thermal effects are modest, but contribute to atmospheric circulation patterns that influence wind, cloud formation, and the distribution of rainfall. The only other world in the solar system with a comparable cycle is Earth, where water evaporates from oceans, forms clouds, falls as rain, flows through rivers, and returns to the oceans in a continuous loop. The parallels between Earth's water cycle and Titan's methane cycle are striking, despite the chemical differences, demonstrating that certain processes emerge naturally whenever the right conditions exist. Stable liquid at the surface, an atmosphere that can hold vapor, and energy to drive evaporation. These cycles create dynamic surfaces rather than static ones, worlds where landscapes evolve and where the same substance exists simultaneously in multiple phases. This hydrocarbon cycle has sculpted Titan's surface over the eons since the Moon reached its current state, creating the diverse landscape we will explore in detail next. The rivers have carved channels, the rain has eroded materials, the winds have deposited particles into dunes, and the combined effects have produced a surface as varied as Earth's despite the alien chemistry and frozen temperatures. Understanding the landscape requires seeing how the cycle has worked over geological time to shape what we observe today. The surface of Titan presents a varied landscape where multiple processes have worked together to create features ranging from vast dune fields to mountain ranges to smooth plains. Near the equator, enormous parallel dunes stretch across thousands of kilometers, dark linear features aligned with the prevailing wind direction. These dunes are not made of silicate sand, as Earth's deserts are, but rather of organic particles that have settled from the atmosphere over millions of years, possibly tholins or other complex hydrocarbons solidified by Titan's cold. The dunes are among Titan's most distinctive features, covering roughly 20% of the surface, and revealing the power of wind to shape terrain even in this cold, distant environment. Individual dunes measure roughly 100 meters in height. From trough to crest, substantial features comparable to large sand dunes on Earth. The spacing between dune crests is typically 1 to 2 kilometers, creating a regular pattern that appears as parallel dark stripes in radar images. The particles composing these dunes are estimated at 200 to 300 micrometers in size, about the width of fine sand grains, though their composition differs completely from terrestrial sand. These organic particles are solid at Titan's temperature, behaving mechanically like sand, even though they are chemically closer to soot or plastic than to rock. The alignment of the dunes reveals information about wind patterns in Titan's equatorial region, showing that winds blow consistently enough to shape these features over geological time. The dunes align roughly east to west, parallel to the equator, indicating that the dominant winds blow along this direction. The consistency of this pattern across thousands of kilometers suggests that large-scale atmospheric circulation, rather than local weather, controls the wind regime in this region. The winds required to move particles into dune formations need not be strong. Even the gentle breezes that characterize Titan's surface can transport fine particles when given enough time. Between the dunes, interdune areas appear lighter in radar images, suggesting a different surface material or texture than the dune crests themselves. These areas may be bedrock exposed between the dune fields, the underlying water ice that forms Titan's solid crust showing through where organic particles have been blown away. Alternatively, the interdune areas might be covered in different materials, perhaps coarser particles that radar interprets differently than the fine organic sand of the dunes themselves. The relationship between dunes and interdune areas reveals a landscape organized by wind into zones of deposition and zones of erosion or exposure. Mountains rise in several regions across Titan, formed from water ice that at -179 degrees Celsius possesses the mechanical strength of granite on Earth. Water, ice this cold, is hard, brittle, and strong, capable of supporting mountains thousands of meters high without collapsing under their own weight. Some peaks reach over 3,000 meters above the surrounding terrain. Substantial elevations that create topographic relief comparable to medium mountain ranges on Earth. These mountains may have formed through tectonic processes that deformed Titan's crust, pushing material upward through forces we do not yet fully understand. The mountains show evidence of erosion, their slopes modified by the action of methane rain and possibly by flowing liquid over geological time. Valleys cut into mountain flanks suggest that liquid has carved channels even at high elevations, draining precipitation downslope toward lower terrain. The erosion proceeds slowly in Titan's low gravity and under the gentle influence of methane rain, but over millions of years, it shapes the topography noticeably. The interplay between tectonic uplift creating mountains and erosion wearing them down produces the observed features, similar in principle to mountain building and erosion on Earth, but operating through different specific mechanisms. Plains cover substantial fractions of Titan's surface, appearing relatively smooth in radar images and suggesting either flat bedrock or accumulated sediments that have filled topographic variations. These plains occur at various elevations, from low-lying areas near sea level to elevated plateaus between mountain ranges. Some plains may be sedimentary deposits, material eroded from highlands and carried by rivers or wind to lower elevations where it settled. The smoothness of these plains indicates that whatever processes formed them operated over large areas, creating uniform surfaces rather than the irregular terrain that impacts or localized erosion might produce. Impact craters are surprisingly rare on Titan compared to most moons and planets in the solar system, with only about 90 identified in radar images of the surface. This scarcity indicates that Titan's surface is young in geological terms, with active processes erasing or burying craters faster than new impacts create them. The atmosphere plays a role in crater scarcity by breaking up smaller incoming meteoroids before they reach the surface, preventing the formation of small craters entirely. The largest craters show evidence of modification by erosion and possibly by sediment infill, their rims softened and their floors partially filled with material transported from elsewhere. The young age implied by the crater count means that Titan's surface has been reworked within the last few 100 million years, refreshed by processes that erase the record of ancient bombardment. Erosion by the methane cycle, deposition of organic materials from the atmosphere, and possibly internal geological processes all contribute to this surface renewal. The combination of processes creates a surface that reflects recent activity rather than preserving a record reaching back to Titan's formation. This dynamic quality makes Titan more similar to Earth than to the cratered static surfaces of bodies like our Moon or Mercury. Channels carved by flowing liquid cut across many regions of Titan's surface, particularly at middle and high latitudes where rainfall is more common. These channels range from small valleys a few hundred meters wide to major river systems several kilometers across and hundreds of kilometers long. The channels show V-shaped cross-sections in some locations, characteristic of erosion by flowing liquid cutting downward into bedrock. In other areas, the channels appear broader and shallower, suggesting filling by sediment or different erosion regimes. The global distribution of channels reveals where liquid flow has been sustained enough to carve permanent features. Possible cryovolcanic features have been identified in several locations, regions that might represent eruptions of liquid water and ammonia from Titan's interior, rather than the silicate lava that Earth volcanoes produce. Cryovolcanism remains speculative on Titan, with no definitive observations of active eruptions, but certain features resemble volcanic constructs and could be explained by the extrusion of liquid from below. If cryovolcanism occurs, it would provide a pathway for material from Titan's interior to reach the surface, potentially replenishing atmospheric methane and transporting other substances from depth. The identification of confirmed cryovolcanism awaits better data or direct observation of activity. The surface materials include both water, ice, which forms the bedrock and structural components of the landscape, and organic compounds that have accumulated over billions of years. The organic materials come from atmospheric photochemistry, the continuous production of complex molecules that eventually settle to the surface as a kind of organic snowfall. This accumulation builds up over time, creating layers of organic material that may be meters or even tens of meters thick in some locations. The organic-rich regolith represents material unique to Titan, a resource that records the Moon's atmospheric chemistry over geological time. Different regions show different dominant processes, creating a mosaic of terrains that reflects the balance between wind, liquid, and possibly internal activity. The equatorial dunes are dominated by aeolian processes, wind shaping the landscape through particle transport. The polar regions are dominated by fluvial processes, with liquid creating lakes, rivers, and erosional features. The mid-latitudes show mixtures of both wind and liquid influence, creating transitional zones where multiple processes compete. This regional variation makes Titan's surface complex, despite the uniformity of temperature and the limited number of processes operating. The landscape exists under conditions of extraordinary cold, where familiar substances behave in unfamiliar ways, and where the chemistry proceeding at the surface and in the atmosphere follows pathways impossible on warmer worlds. Understanding this chemistry, how it works at -179 degrees Celsius, and what products it creates, reveals another layer of Titan's remarkable nature. The cold chemistry of Titan operates according to the same physical laws as warm chemistry, but produces different results, creating an environment we are only beginning to understand. The chemistry of Titan unfolds in an environment where cold dominates every reaction, every phase change, every interaction between substances. Water ice, which melts and flows freely on Earth, behaves on Titan exactly as rock behaves here. Hard, rigid, forming the structural foundation of mountains and plains. The ice is so cold that it possesses crushing strength comparable to granite, resisting compression and deformation across geological time. Mountains made of water ice rise thousands of meters into Titan's orange sky, their peaks as solid and unyielding as any stone mountain on Earth. The ice will never melt at the surface under current conditions, remaining frozen billions of years into the future. Methane exists in a state balanced between its liquid and gas phases, with surface temperatures sitting just above the freezing point, but well below the normal boiling point. The atmospheric pressure keeps methane liquid at temperatures where it would boil away to gas under lower pressure, allowing pools and seas of liquid methane to remain stable at the surface. The methane molecules in the liquid are free to move past one another, giving the substance its liquid character, but the cold keeps this motion sluggish compared to liquids at room temperature. Viscosity is lower than water, making methane flow easily, but the molecules still interact through weak forces that give the liquid its cohesion. Ethane, produced in the atmosphere from methane through photochemical reactions, accumulates over time and mixes with surface methane in the lakes and seas. Ethane has a freezing point of -183 degrees Celsius, just barely below Titan's surface temperature, meaning it remains liquid under all but the very coldest conditions. The mixing of ethane and methane creates solutions where the two substances dissolve into each other, sharing the same liquid phase. The ratio of ethane to methane in different lakes may vary, with some lakes richer in ethane if they have had more time to accumulate this photochemical product without receiving fresh methane input. Nitrogen, the dominant atmospheric gas, remains gaseous at Titan's surface temperature and pressure, though it approaches the boundary where liquefaction could occur. At the coldest locations on Titan, particularly at high elevations during winter, nitrogen might condense into liquid, creating pools of liquid nitrogen in isolated cold traps. This condensation is marginal and likely rare, but it represents another instance of a substance existing near its phase boundary, ready to change state with small variations in temperature or pressure. Most of Titan's nitrogen remains in the atmosphere, providing the pressure that keeps methane liquid and serving as the inert background against which other chemistry proceeds. The cold temperature makes chemical reactions proceed far more slowly on Titan than they would at room temperature on Earth. Reaction rates typically decrease by factors of 2 or more for each 10-degree drop in temperature. A rule of thumb that suggests reactions at Titan's temperature might be thousands or millions of times slower than equivalent reactions in warm environments. This slowness means that substances can coexist on Titan that would react quickly if warmed, preserving metastable states that persist for geological time. The slow chemistry creates a kind of natural deep freeze, storing complex organic molecules that would decompose or react away if temperature rose. Despite the cold, complex chemistry occurs continuously in Titan's atmosphere, driven by solar ultraviolet light that breaks apart methane molecules in the upper atmospheric layers. The methane molecule, composed of 1 carbon and 4 hydrogen atoms, shatters when struck by energetic UV photons, producing fragments that seek new partners among the surrounding gases. Hydrogen atoms might pair up to form hydrogen molecules, which are too light to be held by Titan's gravity, and gradually escape to space. The carbon fragments bond with other atoms and molecules, beginning chains of reactions that build complexity from simple starting materials. Ethane forms when methane fragments combine in specific ways, adding carbon to carbon and hydrogen where needed, creating a molecule with 2 carbon atoms instead of methane's 1. Propane can form through further reactions, building a 3-carbon chain, and longer chains develop through continued processes. Acetylene, with carbon atoms joined by triple bonds, represents another product of methane destruction and recombination. Each of these molecules is created in the atmosphere through photochemistry, reactions powered by sunlight rather than by heat. The variety of products demonstrates the richness of carbon chemistry, even in cold environments. The reactions continue beyond these simple hydrocarbons, producing molecules that incorporate nitrogen from the atmosphere alongside carbon and hydrogen. Hydrogen cyanide forms through certain pathways, bringing nitrogen into the organic chemistry system and opening new avenues for complexity. Amino groups, nitrile groups, and other functional structures develop, creating molecules that approach the complexity of biochemistry despite the absence of life. The atmosphere becomes a natural laboratory for organic synthesis, conducting experiments on a planetary scale and producing results that rain down onto the surface over millions of years. Tholins represent the endpoint of this atmospheric chemistry in a practical sense, complex mixtures of organic molecules that have grown large enough to become aerosols, solid or liquid particles suspended in air. Tholins are not single molecules, but rather collections of many different compounds, typically containing hundreds or thousands of atoms arranged in complicated ways. The reddish-brown color that characterizes tholins comes from their molecular structure, which absorbs blue light preferentially and reflects longer wavelengths. These particles form high in the atmosphere and slowly settle toward the surface, taking months or years to drift down through the thick air. When tholins reach the surface, they become part of Titan's regolith, the layer of loose material covering the solid ice bedrock. The accumulation of tholins over billions of years has deposited substantial amounts of organic material across the surface, particularly in equatorial regions, where the dune fields may be composed primarily of these atmospheric products. The organic layer represents a record of Titan's atmospheric chemistry over geological time, each layer reflecting the conditions when it fell from the sky. The total mass of organic material on Titan's surface is uncertain but potentially enormous, exceeding Earth's total biomass despite being produced entirely through non-biological chemistry. The surface environment is reducing in chemical terms, meaning it contains abundant hydrogen and little oxygen, the opposite of Earth's oxidizing surface environment. This reducing character prevents combustion. Nothing can burn on Titan because there is no oxygen to support the reaction. The organic materials on the surface are thermodynamically capable of reacting with oxygen to release energy, but without oxygen present, they remain stable indefinitely. If oxygen were somehow introduced to Titan's surface, the organic materials would represent tremendous chemical potential energy, though the cold would slow any reactions dramatically. Chemical reactions at the surface proceed through different mechanisms than atmospheric photochemistry, with the solid or liquid phases and the absence of strong UV light creating different conditions. Some reactions may be catalyzed by the water-ice surfaces, which could bring reactants together in ways that allow interactions despite the cold. Liquid methane in the lakes and seas might serve as a solvent for certain reactions, dissolving substances and allowing them to encounter each other in solution. The extent of surface chemistry and what products it might create remain areas of active study and speculation. The interaction between liquid methane and water ice is particularly interesting because methane can dissolve small amounts of water, creating solutions that contain both hydrocarbons and dissolved water molecules. This mixing might allow reactions between compounds that would not normally encounter each other, creating products unique to Titan's environment. The lakes might serve as chemical reactors, where organic molecules dissolved in methane interact over long timescales, building complexity through slow processes invisible to our current observations. What accumulates in these lakes and whether unique chemistry occurs there awaits future missions with the capability to sample the liquids directly. The chemistry of Titan creates an environment rich in the building blocks of life: organic molecules, energy sources in the form of chemical gradients, and complex structures, all without any evidence that life exists. This demonstrates that organic chemistry alone does not produce life, that additional factors or processes are required to cross from complex chemistry to biology. Studying Titan's chemistry helps us understand what conditions are necessary for life and what conditions merely produce interesting chemistry. The distinction between non-living complexity and living systems remains one of science's fundamental questions, and Titan provides a natural laboratory for exploring it. The understanding of Titan's cold chemistry and exotic surface features advanced dramatically when a probe from Earth descended through that orange atmosphere and touched down on the frozen surface, returning data from the only landing ever achieved on an outer solar system moon. The Huygens probe's journey to Titan's surface represents a remarkable achievement in planetary exploration, one that revealed the ground truth beneath the obscuring haze. On the 14th of January 2005, a probe named Huygens entered Titan's upper atmosphere at approximately 1,400 kilometers altitude, beginning a descent that would last about 2.5 hours. The probe had separated from the Cassini orbiter 3 weeks earlier, following a ballistic trajectory toward the moon with no ability to maneuver or correct its course. As Huygens struck the atmosphere at roughly 6 kilometers per second, the friction of air resistance began to slow its descent, generating heat that was absorbed by a protective heat shield designed to protect the delicate instruments within. This phase of entry, when speed dropped from thousands of meters per second to hundreds, lasted only a few minutes. The deceleration forces during atmospheric entry pressed on the probe with tremendous intensity, but the heat shield performed exactly as designed, maintaining structural integrity while temperatures at its surface climbed to extreme values. Once speed had dropped sufficiently, a sequence of parachutes deployed to slow the descent further, allowing instruments to begin their operations and cameras to start capturing images. The main parachute opened at an altitude of approximately 160 kilometers, and a smaller stabilizing chute deployed later to adjust descent rate. The parachutes allowed Huygens to drift slowly down through the atmospheric layers, sampling and measuring as it descended. The instruments aboard Huygens measured atmospheric composition at different altitudes, building a profile of how temperature, pressure, and chemical makeup varied from the upper atmosphere down to the surface. Temperature generally decreased from the upper stratosphere through the tropopause before leveling off in the lower atmosphere, while pressure increased steadily as the probe descended deeper into the thickening air. Methane abundance varied with altitude, more concentrated in certain layers, where condensation and evaporation processes concentrated it. The data revealed the detailed structure of Titan's atmosphere in ways that remote observation could not, providing ground truth for atmospheric models. Cameras operating during the descent captured images through the haze, revealing the surface gradually as the probe dropped lower. At high altitudes, the view showed only vague dark and light regions through the thick orange atmosphere, surface features obscured by hundreds of kilometers of intervening haze. As Huygens descended below about 60 kilometers altitude, clearer features became visible. Channels cutting across brighter terrain, networks of valleys converging and joining, and dark regions that appeared to be lower-lying plains. The images revealed a landscape shaped by flowing liquid, with erosional features unmistakable even in the hazy, low-contrast views. The channels visible from altitude showed branching patterns characteristic of drainage networks, smaller tributaries joining into larger channels that led toward dark lowland areas. Some regions appeared to be coastlines, boundaries between brighter, elevated terrain and darker, low-lying areas that might be filled with liquid or covered in organic sediments. The images suggested that Huygens was descending toward what had once been a river drainage system, perhaps now dry, but clearly carved by flowing liquid over extended time. The features became clearer and more detailed as altitude decreased, and the camera's field of view narrowed to show smaller areas in higher resolution. The landing site, in a region called Adiri, located about 10 degrees south of the equator, was approaching rapidly as Huygens drifted down through the final kilometers of descent. The surface appeared relatively flat from lower altitudes, showing scattered bright features against a darker background, possibly rocks or ice blocks scattered across sediments. The final moments before landing showed the surface rushing up to meet the camera, details resolving into individual features before the images stopped as the probe contacted the ground. The touchdown occurred at approximately 4.5 meters per second, gentle enough that the probe survived intact. The impact, when Huygens struck Titan's surface, compressed the ground beneath it, and instruments measuring the deceleration revealed information about the surface material's consistency. The surface yielded slightly under the probe's weight, behaving like wet sand or clay on Earth, firm enough to support the spacecraft, but not as rigid as solid rock. The penetrometer, an instrument designed to measure surface properties during impact, recorded data suggesting a crust of material overlying something softer below. The probe settled into the surface slightly, its weight creating a small indentation, and remained stable without sinking further. From the surface, the camera captured images of the immediate surroundings, the only photographs ever taken from the ground on Titan. The view showed a relatively flat plain extending to the horizon in all directions, scattered with rounded objects that appeared to be ice rocks or pebbles. These objects, probably chunks of water ice, smoothed by transport in flowing liquid, lay partially embedded in the darker surface material around them. The rocks were roughly 10 to 20 centimeters in size, large enough to be clearly visible, but small enough that flowing liquid could have moved them. Their rounded shapes suggested erosion, the wearing away of edges and corners through tumbling or abrasion. The surface material between the rocks appeared darker, possibly organic-rich sediments or fine-grained material deposited by liquid that had since evaporated or drained away. The contrast between the brighter ice rocks and the darker sediment created a mottled appearance, a landscape of light and dark patches extending outward from the landing site. The lighting was dim, the orange sky providing only faint illumination, creating a scene that appeared perpetually twilight. The sun was not visible as a distinct disk, but rather as a diffuse glow somewhere in the hazy sky, too faint and scattered to create sharp shadows. Temperature measurements from the surface confirmed the steady -179 degrees Celsius that characterizes Titan's surface environment. Cold beyond any ordinary terrestrial experience, but exactly as predicted from orbital observations. The atmospheric pressure, measured at the surface, matched expectations as well, roughly 1.5 times Earth's sea level pressure. The composition of the air immediately above the surface showed the expected dominance of nitrogen, with methane comprising the next most abundant component. Everything measured at the surface aligned with what models and remote sensing had suggested, validating decades of theoretical work. Huygens operated on the surface for about 72 minutes, transmitting data continuously to the Cassini orbiter passing overhead. The probe's battery and instruments were designed for this limited operational period, with no expectation that the harsh surface environment could be endured for longer. During those 72 minutes, cameras continued to record the scene. Spectrometers analyzed surface composition, and various sensors measured conditions. The data flowed up to Cassini, which recorded everything and later transmitted it back to Earth, preserving the information from this brief ground-level visit. The descent images and surface photographs together provided the first ground truth about what Titan looks like beneath its hazy atmosphere, confirming that the radar interpretations were correct and that this moon possesses a landscape shaped by familiar processes. The channels were real, the drainage networks existed, the surface showed evidence of liquid transport and erosion. The rounded ice pebbles spoke of movement and wearing, of forces that had shaped them over time. The sediments suggested deposition, the accumulation of fine material carried by liquid or wind. Everything pointed to an active surface, modified by ongoing processes, rather than frozen in ancient stasis. After transmitting its final data packets, Huygens fell silent as its battery expired and the cold finally overwhelmed its systems. The probe remains on Titan's surface today, settled into that sediment plain among the rounded ice rocks, a human artifact on a world nearly 1 billion miles from Earth. The data it returned during its brief operation transformed our understanding of Titan from a theoretical construction based on remote observations to a real place we had visited, measured, photographed, and touched. The success of Huygens demonstrated that landing on outer solar system bodies was possible, that parachutes would work in thick atmospheres, and that carefully designed instruments could survive and operate in these extreme environments. The Huygens landing provided one snapshot of one location, a single point of ground truth on a world whose surface area equals nearly 2 Earths. Understanding Titan globally required the patient work of the Cassini orbiter, which would spend 13 years flying past the moon repeatedly, mapping its surface through radar, and watching as seasons changed and the hydrocarbon cycle proceeded through its long yearly rhythm. The Cassini spacecraft arrived at Saturn in July 2004, after a journey of nearly 7 years from Earth, entering orbit around the ringed planet to begin a mission originally planned for 4 years, but ultimately extended to 13. Titan was a primary target throughout Cassini's long mission, with the moon's thick atmosphere and hidden surface demanding repeated observations using multiple instruments. The spacecraft was designed to see through Titan's obscuring haze, using radar and infrared wavelengths, revealing the surface features that visible light could not penetrate. Over the mission's duration, Cassini would complete 127 targeted flybys of Titan, each one providing opportunities to map new areas or revisit known regions to check for changes. The radar instrument aboard Cassini functioned by sending microwave pulses toward Titan's surface and measuring the reflections that bounced back. Different surface materials and textures reflect radar differently, with smooth surfaces appearing dark and rough, or tilted surfaces appearing bright. Liquid surfaces appear very dark because they reflect radar away at specific angles rather than scattering it back toward the spacecraft. By building up radar images, strip by strip during successive flybys, Cassini gradually mapped about 80% of Titan's surface, with varying levels of detail. The radar revealed mountains, dunes, rivers, lakes, and plains that had been completely invisible to all previous observations. The first clear evidence that liquid existed on Titan's surface came from radar observations in 2006, when images from the North Polar region showed features with the characteristic signature of smooth, liquid surfaces. These dark patches had shorelines defining their boundaries, and their radar properties matched predictions for liquid methane and ethane. The discovery confirmed what many scientists had suspected but could not prove: that stable liquid hydrocarbons pooled at the surface, creating lakes and seas in the polar regions. The finding answered a long-standing question about where Titan's methane might be stored, and revealed that the moon truly had a liquid cycle operating at its surface. Continued observations over subsequent years built up detailed maps of the northern lakes and seas, revealing their sizes, shapes, and distributions. Kraken Mare emerged as the largest feature, its extent becoming clear only after multiple passes stitched together a complete image. Ligeia Mare and Punga Mare appeared as substantial bodies in their own right, each with complex shorelines and associated river networks draining into them. The southern polar region showed far fewer lakes, with Ontario Lacus standing as the most prominent southern feature. The asymmetry between north and south polar liquid distribution became one of Titan's puzzling characteristics, still not fully explained, even as observations documented it in detail. The visual and infrared mapping spectrometer, another instrument aboard Cassini, observed Titan at wavelengths where the atmospheric haze is relatively transparent. These infrared observations revealed surface features through the atmosphere, showing variations in composition and temperature across different regions. The spectrometer identified different materials on the surface, distinguishing between water ice, organic-rich terrains, and liquid-filled lakes through their spectral signatures. The infrared data complemented the radar observations, providing chemical information to accompany the structural information that radar supplied. Seasonal changes became apparent as Cassini observed Titan over multiple years, watching as northern spring progressed into northern summer. Cloud activity increased in the northern polar region as temperatures rose and evaporation from the northern seas strengthened. The clouds appeared as bright features in infrared images, their methane composition creating strong spectral signatures. The clouds formed, drifted with winds, and sometimes produced rain that darkened the surface below when the liquid fell and wetted the ground. The seasonal progression demonstrated that Titan's hydrocarbon cycle responded to changes in sunlight distribution, becoming more vigorous during summer and quieter during winter. Small lakes in the southern polar region appeared to change between observations, separated by several years, with some features present in early images vanishing in later ones. These disappearances suggested evaporation, the lakes drying up as methane escaped into the atmosphere during southern summer and was not fully replenished by rainfall or river input. The northern lakes, in contrast, appeared to fill during northern summer, their shorelines advancing as increased rainfall and river flow delivered more liquid than evaporation removed. The observations revealed a dynamic system where liquid moved between different reservoirs on timescales of years, responding to seasonal forcing. Radio science experiments conducted during close flybys measured Titan's gravity field with high precision, tracking how the Moon's gravity pulled on Cassini's trajectory. These measurements revealed information about mass distribution within Titan's interior, showing that the interior was not uniform. The gravity data indicated that Titan's interior included less dense components mixed with, or layered beneath, the solid outer ice shell. The interpretation that fit best involved a subsurface ocean of liquid water, which would be less dense than the high-pressure ice that might lie below it. The gravity measurements provided one line of evidence for this hidden ocean. A second line of evidence for the subsurface ocean came from precise tracking of Titan's rotation as it orbited Saturn. Cassini's radar measured the positions of surface features during multiple flybys over several years, revealing that the surface position changed slightly in a cyclical pattern. This wobble, called libration, happened because the ice shell was not rigidly attached to the interior, but could shift slightly as tidal forces from Saturn varied during Titan's slightly elliptical orbit. A completely solid moon would not show this wobble. The shell and interior would move together as one unit. The detected wobble could only occur if a liquid layer decoupled the shell from the deeper interior. The combination of gravity measurements and libration observations convinced scientists that Titan harbors a global ocean of liquid water beneath its ice shell. Perhaps 50 to 100 kilometers below the surface we can see. This ocean is separate from the surface methane system, existing in complete darkness at temperatures near the freezing point of water. The ocean probably contains dissolved ammonia serving as antifreeze, allowing liquid to exist at temperatures slightly below 0 Celsius. The discovery of this ocean added Titan to the list of ocean worlds in the outer solar system, joining Jupiter's moons Europa and Ganymede and Saturn's small moon Enceladus as bodies where liquid water exists beneath ice. Cassini's long mission allowed observations spanning half of Titan's year, watching as northern winter transitioned to northern summer and observing the changes this progression brought. Cloud patterns shifted with the seasons, concentrated in the summer hemisphere where evaporation was strongest. Surface features remained stable over the mission duration, showing that the landscape changes slowly despite the active hydrocarbon cycle. The dunes, mountains, and plains observed in early mission images looked essentially the same in images taken years later, indicating that Titan's surface evolution proceeds over timescales longer than decades or even centuries. The mission discovered atmospheric phenomena beyond simple cloud formation, including massive storms that occasionally developed and produced intense precipitation over limited areas. One such storm occurred in 2010, appearing in the southern hemisphere during southern autumn and producing effects visible both in infrared images of clouds and in radar images that showed surface darkening where rain fell. The storm demonstrated that Titan's weather can produce episodic intense events in addition to the gentle rain that appears more common. The capacity for storms suggests that Titan's hydrocarbon cycle can operate in different modes, sometimes quietly and sometimes more vigorously. Cassini also observed Titan in various wavelengths beyond radar and infrared, including ultraviolet observations of the upper atmosphere and magnetospheric measurements of how Titan interacts with Saturn's magnetic field. The ultraviolet data revealed atmospheric chemistry in action, showing the distribution of various molecules produced through photochemistry. The magnetospheric observations showed how Titan's atmosphere creates a boundary with Saturn's magnetosphere, deflecting the flow of charged particles around the Moon and creating a wake downstream. These observations painted a complete picture of Titan as a complex system where atmosphere, surface, and interior all interact and influence one another. The mission ended in September 2017 when Cassini, low on fuel and unable to continue orbital maneuvers, was deliberately plunged into Saturn's atmosphere to prevent any possibility of the spacecraft eventually crashing into Titan or Enceladus. Protecting these potentially habitable worlds from contamination by Earth microbes that might have survived on the spacecraft was deemed more important than preserving the spacecraft itself. As Cassini descended into Saturn's clouds, it transmitted data until the very end, concluding one of the most successful planetary missions ever flown. The data returned during 13 years of operation will support scientific analysis for decades to come. The discoveries made by Cassini transformed Titan from a mysterious haze-wrapped moon into a world we could map, understand, and compare to Earth. The mission revealed the surface liquid, documented the hydrocarbon cycle, discovered the subsurface ocean, and established Titan as one of the solar system's most fascinating and complex worlds. Everything we know about Titan's surface features, its weather, its seasons, and its interior structure comes directly from Cassini's patient observations and the scientists who analyzed the data. What remains to be discovered will require new missions, new instruments, and continued dedication to exploring this remarkable moon. Beneath the solid ice crust that forms Titan's outer shell, below the organic-rich surface materials, and beneath perhaps 50 to 100 kilometers of frozen water ice, lies a realm utterly different from the methane lakes and orange skies above. A global ocean of liquid water wraps around Titan's interior, possibly reaching depths of 100 kilometers or more before transitioning to other materials below. This ocean has existed in complete darkness since its formation, isolated from sunlight by the thick ice shell above it, warmed not by the distant sun, but by internal heat sources that keep water liquid despite the frigid surface far above. The evidence for this ocean emerged gradually as Cassini gathered data over years of observations, two independent lines of measurement converging on the same conclusion. The gravity measurements revealed that Titan's interior mass was distributed in a way that required less dense material somewhere between the surface and the deep interior. Solid ice of various high-pressure forms could account for some structure, but the best match to the gravity data involved a layer of liquid water. Liquid water is less dense than high-pressure ice forms, creating the measured gravity signature when included in models of Titan's interior structure. The libration measurements confirmed what gravity suggested, showing that the ice shell floated freely enough to shift position slightly in response to tidal forces. The surface features tracked by radar moved in their positions relative to Titan's center of mass, wobbling back and forth by about 10 meters over the course of an orbit around Saturn. This motion could only occur if the ice shell was decoupled from the interior by a liquid layer. The shell essentially floats on the ocean, able to shift position, while the deeper interior maintains a more stable orientation relative to Saturn. The decoupling proved that liquid existed beneath the ice. The depth at which the ocean begins depends on the thickness of the ice shell above it, which is estimated but not precisely known. Models suggest the ice shell might be 50 to 100 kilometers thick, meaning the ocean begins at this depth and extends downward from there. The ocean's lower boundary is more uncertain, depending on what phases of ice or rock exist at the high pressures in Titan's deep interior. The ocean might extend for tens of kilometers before pressure forces water into exotic ice forms that exist only under conditions never experienced on Earth's surface. Temperature within the ocean is constrained by the presence of liquid water itself, which requires temperatures above water's freezing point at the relevant pressure. The freezing point of water increases with pressure, meaning deeper parts of the ocean need higher temperatures to remain liquid than shallower parts would. At the ice-ocean boundary, temperature is probably close to 0 Celsius or slightly below, kept from freezing by dissolved substances that depress the freezing point. Ammonia is the most likely antifreeze component, mixed into the water at concentrations perhaps reaching 5 to 15% by mass. Ammonia's presence in the ocean would allow water to remain liquid at temperatures several degrees below 0 Celsius, expanding the range of conditions where the ocean can exist. Ammonia is common in the outer solar system, present during the formation of moons from the disk of material around young Saturn. As Titan's interior warmed and differentiated, ammonia would have been incorporated into the water, creating the ammonia-water ocean we infer today. The mixture behaves differently than pure water, with altered viscosity and different thermal properties, but it remains fundamentally a liquid water environment, even with ammonia present. The ocean is global, wrapping completely around Titan beneath the ice shell, though its thickness may vary with latitude or longitude if the ice shell thickness varies. A global ocean is more stable than isolated pockets of liquid would be, maintaining consistent pressure and temperature throughout its extent. The total volume of this ocean likely exceeds the volume of liquid in all of Titan's surface, methane lakes and seas combined by factors of thousands, making the subsurface ocean the dominant liquid reservoir on the Moon. The ocean contains more water than the surface contains hydrocarbons, reversing what someone familiar only with the surface would expect. The ocean's existence depends on internal heat sources, maintaining temperatures above freezing despite the cold surface far overhead. Two potential heat sources are available: radioactive decay of elements in Titan's rocky core and tidal heating from gravitational interactions with Saturn. Radioactive decay releases heat continuously as unstable isotopes of potassium, uranium, and thorium break down over billions of years, This heat flows outward from the core, through the mantle, and into the overlying water, warming it from below. The heat flow is modest but persistent, maintaining elevated temperatures over geological time. Tidal heating results from Titan's orbit around Saturn, which is slightly elliptical rather than perfectly circular. As Titan moves closer to and further from Saturn during each orbit, Saturn's gravitational pull varies in strength, flexing Titan's interior slightly. This flexing generates heat through friction, warming the interior in a process similar to how repeatedly bending a wire back and forth heats it. The amount of tidal heating on Titan is small compared to Jupiter's moon Io, but it contributes to the total heat budget that maintains the ocean. The combination of radioactive and tidal heating appears sufficient to prevent the ocean from freezing over geological time. The ocean sits between two boundaries, the ice shell above and either more ice or rock below, defining its vertical extent. The upper boundary, where ocean meets ice, is a phase transition from liquid to solid at approximately 0 degrees Celsius, though the exact temperature depends on ammonia concentration and pressure. This boundary might not be perfectly smooth. Variations in temperature or ice thickness could create topography on the underside of the ice shell, with deeper sections projecting down into the ocean and shallower sections creating overhead depressions when viewed from below. The lower boundary is more uncertain, potentially transitating to high-pressure ice or reaching the rocky mantle directly. The environment within the ocean is utterly dark, no sunlight penetrating through the overlying ice to illuminate the water. Any organisms living in this ocean would need to exist without photosynthesis, deriving energy from chemical reactions as deep-sea life on Earth does at hydrothermal vents. The ocean chemistry depends on what substances dissolve from the ice above or the rock below, potentially including salts, dissolved gases, and organic molecules, if any, manage to penetrate down through the ice shell. The composition determines what reactions are possible and what energy sources might be available to hypothetical life. Circulation within the ocean likely occurs driven by temperature differences between the relatively warm deep waters and the colder water near the ice ceiling. Convection would create currents carrying water from depth toward the ice boundary and back down again, mixing the ocean and distributing heat and dissolved substances. The circulation patterns depend on ocean depth, temperature gradients, and the presence of Coriolis forces from Titan's rotation. Modeling these circulation patterns helps predict where different chemical environments might exist and where energy sources might concentrate. The possibility of hydrothermal activity at the ocean floor, where water meets rock, remains speculative but intriguing. On Earth, hydrothermal vents support rich ecosystems in the deep ocean, providing both heat and chemical energy that sustain life in complete darkness. If Titan's ocean contacts a rocky seafloor, and if that rock is warm enough, similar hydrothermal systems might operate, releasing minerals and heat into the overlying water. These vents could provide energy sources for hypothetical life forms, creating habitable niches in an otherwise energy-poor environment. Whether Titan actually has hydrothermal vents depends on interior structure and heat flow that we cannot yet measure. The ocean is isolated from the surface methane system by the thick ice shell, preventing exchange of materials between the two liquid reservoirs. Organic molecules produced in the atmosphere and deposited on the surface do not easily reach the ocean, blocked by kilometers of solid ice. Similarly, substances dissolved in the ocean cannot reach the surface unless some transport mechanism moves them through the ice. This isolation means the ocean and surface environments are chemically distinct, each with its own inventory of materials and its own set of possible reactions. The two liquid systems coexist on the same moon, but essentially do not interact. The stability of the ocean over billions of years provides a potentially habitable environment that has persisted since early in Titan's history. Unlike the surface, which experiences seasonal changes and variations in liquid availability, the ocean maintains constant conditions over geological time. This stability might favor the development of life if appropriate chemical building blocks and energy sources are available. However, the isolation from surface organics and the limited energy supply present challenges that Earth's ocean does not face. Whether life exists in Titan's ocean remains pure speculation, with no evidence either supporting or ruling out the possibility. Understanding the ocean's properties and potential habitability motivates interest in future missions that might penetrate the ice shell and sample or explore the water beneath. Such missions lie far in the future, requiring technology that does not yet exist and overcoming formidable challenges. For now, the ocean remains inferentially understood through gravity and rotation measurements, a hidden realm we know exists but cannot yet directly observe. What discoveries await in those dark waters, if we ever reach them, remains one of Titan's greatest mysteries. The possibility that life might exist there, or in the methane lakes above, makes Titan one of the most interesting targets in the search for life beyond Earth. The question of whether life exists on Titan emerges naturally from the moon's chemistry and the presence of two distinct liquid environments where biological processes might conceivably operate. Titan is rich in organic molecules, carbon-based compounds that on Earth form the foundation of all living things. Though on Titan, these molecules are produced through atmospheric chemistry rather than by biology. The atmosphere continuously manufactures complex organics from simple methane through chains of photochemical reactions, creating substances that rain down onto the surface and accumulate over geological time. This organic inventory provides raw materials that life might use if life could exist in Titan's extreme conditions. The surface methane lakes present an environment utterly unlike anything familiar from Earth biology. Liquid hydrocarbons at temperatures where Earth life would freeze instantly. Life as we know it requires liquid water as a solvent, the medium in which biochemical reactions occur and in which cells maintain their structure. Methane is a very different solvent than water, with different properties that would support different kinds of chemistry. Whether biochemistry could operate in liquid methane instead of liquid water remains an open question, one that scientists approach through theoretical modeling and laboratory experiments rather than through any actual observations of methane-based life. The fundamental challenge for methane-based life involves constructing cell membranes that remain flexible in liquid methane at temperatures below -170 degrees Celsius. On Earth, cell membranes are made of lipid molecules that arrange themselves into flexible sheets, creating barriers that separate the cell interior from the external environment while allowing selective passage of certain substances. These lipid membranes work in liquid water but would freeze solid in liquid methane, losing the flexibility necessary for cellular function. Alternative membrane materials would be needed, substances that remain flexible at Titan's cold temperatures, while maintaining the barrier and selective permeability that cells require. Researchers have proposed hypothetical membrane structures called azotosomes, molecules containing nitrogen that might form stable membranes in liquid methane. These theoretical structures have been studied through computer modeling, which suggests they could potentially function as cell boundaries in Titan's environment. Whether such membranes could actually form, and whether they could support the functions that biological membranes perform, remains unknown. The models demonstrate possibility rather than actuality, showing that the laws of chemistry do not forbid methane-based life, but stopping short of proving it could exist or does exist. Energy sources for hypothetical methane-based life present another challenge, as the cold temperature drastically slows chemical reactions that might release useful energy. On Earth, life extracts energy from chemical reactions that would occur spontaneously but slowly, using biological catalysts to speed the reactions and capturing the released energy before it dissipates as heat. In liquid methane, at Titan's temperature, reactions would proceed perhaps thousands or millions of times slower than equivalent reactions on Earth. Life would need to operate on these extremely slow timescales, or find ways to catalyze reactions enough to overcome the temperature barrier, or utilize energy sources we have not considered. The availability of oxidants, substances that can accept electrons in chemical reactions, is limited in Titan's reducing atmosphere and surface environment. On Earth, oxygen serves as the primary oxidant for most life, accepting electrons in reactions that release substantial energy. Titan has no free oxygen, its atmosphere dominated by nitrogen and its surface by hydrocarbons. Alternative oxidants might exist in limited quantities, perhaps brought down from the upper atmosphere, where photochemistry produces more exotic species. The scarcity of oxidants would severely limit the energy available to methane-based life, creating a harsh metabolic environment compared to Earth's oxygen-rich surface. The subsurface ocean presents a different possible environment for life, one more familiar from Earth's perspective, though still challenging in its own ways. Liquid water ocean with dissolved minerals and possible organic molecules resembles environments where life exists on Earth, particularly in the deep sea, where sunlight never reaches. The temperature near the ocean ice boundary would be close to 0 Celsius, cold by our standards, but within the range where Earth organisms can function. Some Earth bacteria thrive at temperatures near freezing, demonstrating that water-based biochemistry can operate in very cold conditions if water remains liquid. Energy sources in the subsurface ocean could potentially include chemical reactions at a rocky ocean floor, if one exists, analogous to Earth's hydrothermal vents, where heat and minerals support rich ecosystems. The reactions between warm rock and cold ocean water release chemicals that microorganisms can use as energy sources, processes that require no sunlight and could operate in Titan's dark ocean if appropriate conditions exist. The ocean would need contact with warm rock and active circulation to deliver reactive chemicals to organisms, conditions that may or may not exist depending on Titan's interior structure. The isolation of the subsurface ocean from the surface organic chemistry creates a challenge for any ocean-based life, as the abundant organic molecules at the surface cannot easily reach the ocean through the thick ice barrier. Life in the ocean would need to build organic molecules from simpler starting materials dissolved in the water, possibly carbon dioxide or methane leaking from the interior. This requirement limits the chemical resources available compared to what surface or atmospheric chemistry provides. The ocean may be richer in energy, but poorer in organic materials than the surface lakes, creating a different set of constraints on possible life. No evidence currently exists for life in either of Titan's liquid environments, surface or subsurface, and no observations have been made that require biology as an explanation. The organic chemistry we observe in the atmosphere and on the surface can be explained entirely through photochemistry and other non-biological processes. The detection of any chemical that appeared to be produced by life, or the observation of any pattern suggesting biological organization, would be extraordinary findings that would transform our understanding. So far, nothing observed demands biological interpretation. The search for life on Titan would require measuring specific chemical signatures that biology produces, but non-biological chemistry typically does not. On Earth, life creates certain molecular patterns, particular arrangements of atoms, specific chirality in organic molecules, isotopic ratios that differ from non-biological sources. Detecting similar patterns on Titan might suggest biological activity, though non-biological explanations would need to be ruled out carefully. The chemistry on Titan is so active and so complex that many molecules exist that also exist in Earth life, but their presence alone proves nothing about biology. Future missions to Titan could search for biosignatures in the methane lakes or in materials brought to the surface from depth. Analyzing lake composition in detail might reveal chemical disequilibria that suggest metabolism, concentrations of certain molecules that exceed what chemistry alone would produce. Examining sediments and organic deposits could reveal patterns or structures that hint at organization beyond chemistry. The search would be difficult, requiring instruments sensitive enough to detect subtle signals among the complex background of non-biological organics. False positives and ambiguous results would be expected, making definitive conclusions challenging. The question of life on Titan illustrates how much we still do not understand about life itself, what minimal requirements allow it to exist, how it begins from non-living chemistry, what environments can support it. Titan serves as a natural laboratory for exploring these questions, a place where complex organic chemistry proceeds without biology, demonstrating that chemistry alone creates complexity. If life does exist on Titan, it would expand our understanding of life's possibilities dramatically. If life does not exist, despite the organic richness and liquid environments, that absence would teach us about what additional factors life requires beyond chemistry and liquid. The study of Titan provides another perspective beyond the search for life, one that connects this distant frozen moon to our own planet's distant past. Titan's atmosphere and chemistry may resemble Earth as it was more than 4 billion years ago, before life transformed our world. Understanding Titan helps us understand the early Earth and the chemical processes that preceded biology here. The Earth that existed 4 billion years ago bears little resemblance to the planet we know today, and studying that ancient world presents enormous challenges. The rock record has been recycled through plate tectonics, destroying most direct evidence of conditions before life transformed the planet. The atmosphere has changed completely. The surface chemistry operates by entirely different rules, and the sun itself was dimmer then. Yet far out in the cold reaches of the solar system, a moon orbits Saturn that may preserve conditions remarkably similar to those vanished early Earth environments. Titan's atmosphere consists primarily of nitrogen gas, roughly 90% of the total, with methane making up most of the remainder. Earth's early atmosphere, before oxygen-producing life appeared, contained substantial nitrogen and likely significant amounts of methane as well, released from volcanic activity and chemical reactions. The similarity in composition creates parallel environments, despite the vast difference in temperature between warm early Earth and frozen Titan. Both atmospheres wrapped their worlds in thick blankets of nitrogen, setting the stage for complex chemistry driven by sunlight from above. The methane in both atmospheres becomes crucial because sunlight breaks it apart, starting chemical cascades that build larger and more complex molecules. On Titan today, we observe this process directly as ultraviolet light from the distant sun strikes methane molecules high in the atmosphere. The methane splits into fragments, individual carbon and hydrogen atoms, or small clusters, which then recombine in various ways. Some reform into methane, but others build into ethane, propane, acetylene, and dozens of other hydrocarbons, each one more complex than the original. These reactions continue upward in complexity, the molecules growing larger and incorporating nitrogen from the atmosphere into their structures. Eventually, the chemistry produces tholins, those complex organic molecules that give Titan's haze its orange color and represent some of the most sophisticated non-biological chemistry occurring anywhere. The same progression almost certainly occurred in Earth's early atmosphere, building up organic molecules from simple starting materials. On Earth, these molecules rained down into warm oceans where they accumulated and potentially contributed to the origin of life itself. You are listening to The Drowsy Astronaut, and tonight we continue our gentle journey through Titan's alien landscape by exploring how this frozen moon connects to Earth's deep past. The comparison teaches us about our own planet's history, about chemistry that preceded biology, and about what worlds look like before life emerges. There is no rush in what follows, just a slow exploration of connections across time and space. Facts delivered softly as our attention turns to these parallel atmospheres. The organic haze that obscures Titan's surface from visible light probably resembled haze that existed in Earth's early atmosphere, though the evidence from Earth is mostly indirect. Chemical models of early Earth's atmosphere predict that organic haze should form under conditions similar to what we observe on Titan today. Some researchers even call Titan a laboratory for studying early Earth, a natural experiment running in slow motion at Saturn. The cold preserves molecules that would react quickly in Earth's warmth, allowing us to study intermediate steps in organic chemistry that early Earth passed through rapidly. Both worlds experience weather driven by evaporation and condensation, though the substances differ dramatically between warm Earth and cold Titan. On Titan, methane evaporates from lakes, rises into the atmosphere, condenses into clouds, and falls as rain, completing a cycle directly analogous to Earth's water cycle. On early Earth, water performed this same cycle even then, but methane may have also cycled through the atmosphere in similar patterns. The presence of active weather systems on both worlds means erosion, transport of materials, and ongoing reshaping of the surface through atmospheric processes. The similarity extends to the presence of rivers, lakes, and possibly coastlines shaped by liquid flowing across solid surfaces. Titan's rivers of methane cut channels through water ice and organic-rich terrain, depositing sediments and creating deltas where they meet the lakes. Early Earth's rivers of water performed identical functions in principle, cutting through rock, transporting sediment, creating the features familiar from river systems. The fundamental physics of liquids flowing downhill under gravity creates parallel outcomes despite the completely different chemical compositions involved. One critical difference separates Titan from early Earth more than any other factor. Temperature determines which molecules can exist as liquids and which remain frozen solid. On Titan, at -179 degrees Celsius, water is rock and methane flows, while on early Earth, at temperatures perhaps similar to today, water flowed and methane stayed gaseous. This temperature difference means the two worlds operate similar cycles with different substances, like two orchestras playing the same music with different instruments. The pattern is the same, but the sound differs completely. The energy available for chemistry also differs substantially between the two worlds, with early Earth receiving far more sunlight than Titan does today. Earth orbits much closer to the Sun, gathering roughly 100 times more solar energy per square meter than Titan receives at Saturn's distance. This extra energy powers faster chemical reactions, more vigorous weather, and greater rates of erosion and deposition. Titan's chemistry proceeds in slow motion by comparison, the cold and the dim light combining to stretch processes over much longer timescales. Despite receiving less energy, Titan's thick atmosphere traps some of the meager warmth it does receive through a modest greenhouse effect. Methane in the atmosphere absorbs infrared radiation, trying to escape from the surface, redirecting some of it back downward and warming the surface by perhaps 10 or 20 degrees above what it would otherwise be. This greenhouse warming keeps Titan's surface just warm enough for methane to exist as liquid rather than being frozen solid, enabling the entire hydrocarbon cycle. Early Earth similarly benefited from greenhouse gases, including methane, which helped maintain liquid water despite the sun being dimmer than it is today. The organic molecules accumulating on Titan's surface over millions of years create deposits that have no exact equivalent on modern Earth. Our planet's surface is constantly being recycled and oxidized, organic materials being broken down by oxygen in the atmosphere and by biological activity. Titan has no oxygen and no life, so organic molecules can accumulate indefinitely, building up layers that represent millions of years of atmospheric chemistry settling to the ground. These deposits may resemble what existed on Earth before oxidation became dominant, preserving a record of pure organic chemistry. The dunes near Titan's equator, made of organic particles rather than mineral sand, offer a window into what landscapes might look like when complex organic chemistry runs for millions of years, with no biology to interrupt it. The particles forming these dunes are likely tholins, mixed with water ice, darkened by radiation and shaped by wind into elegant parallel formations. On early Earth, similar organic-rich sediments may have covered parts of the surface, waiting for the chemical innovations that would eventually spark life. Whether any of Titan's accumulated organics show chemical patterns approaching biological organization remains an open and fascinating question. Studying Titan helps scientists refine their understanding of what prebiotic chemistry can achieve without life's intervention, establishing baselines for what to expect on lifeless worlds. The Moon demonstrates that complex organic molecules form readily under certain atmospheric conditions, that weather and erosion can operate without biology, and that diverse landscapes develop through purely physical and chemical processes. These lessons apply not just to understanding Earth's past, but also to interpreting observations of planets around other stars, worlds we can study only from great distances. The timeline separating Titan from early Earth spans billions of years and involves completely different evolutionary paths. Yet both illustrate what happens when nitrogen-methane atmospheres exist on solid worlds. Early Earth progressed beyond this stage, when life appeared and oxygen began accumulating in the atmosphere roughly 2.5 billion years ago. Titan remains frozen in what may be an earlier chapter, its chemistry continuing along tracks that Earth abandoned when biology took over. The comparison is imperfect but illuminating, offering perspective on both worlds. Looking across Titan's landscape, the methane rivers cutting through organic rich plains, the orange haze filtering weak sunlight, the lakes reflecting radar back to distant spacecraft. We see processes that may once have operated on Earth. The specific molecules differ, the temperature varies enormously, and billions of years separate the two scenarios. Yet, the fundamental patterns remain recognizable. Cycles of evaporation and rain, rivers flowing to seas, organic chemistry building complexity from simple ingredients. Titan shows us what a world with active chemistry but no biology looks like, perhaps offering glimpses into Earth's own deep history. Understanding Titan more completely, unraveling the details of its chemistry and its cycles, and its potentially habitable ocean far below, will require returning with new instruments and new approaches. The Cassini mission provided extraordinary insights over 13 years of observation, but it observed from orbit and through Huygens's brief visit to the surface. The next step in exploring this remarkable moon involves a mission unlike any attempted before, a flying robot that will hop from site to site across Titan's alien landscape. Plans for returning to Titan took shape as the scientific community absorbed Cassini's discoveries and recognized how much more could be learned through direct surface exploration. Among various proposals for future missions, one stood out for its innovative approach and scientific potential, earning selection by NASA in 2019. The mission is called Dragonfly, and it will explore Titan in ways that seem almost fantastical, yet are made practical by the moon's unique environment of thick air and gentle gravity. Dragonfly is not a rover that must crawl slowly across rough terrain, pausing to study rocks within reach of its instruments. Instead, it is a rotorcraft, essentially a large drone powered by 8 rotors that will allow it to fly through Titan's thick atmosphere. The design resembles certain dual quadcopter drones used on Earth, with rotors arranged to provide stability and redundancy. If one rotor fails, the remaining 7 can still maintain controlled flight, an important safety feature for a mission operating billions of kilometers from any possibility of repair. The choice to fly rather than drive makes particular sense at Titan because the atmosphere is so much thicker than Earth's, and the gravity so much weaker. Titan's surface gravity is only about 14% of Earth's gravity, meaning everything weighs much less and requires less force to lift. At the same time, the atmospheric density at the surface is about 4 times higher than Earth's atmosphere at sea level, providing substantial support for rotors or wings. These conditions combine to make flying easier on Titan than on Earth, requiring less power to stay aloft. The mission will launch in 2028 if schedules hold, beginning a journey that will take roughly 6 years to cover the vast distance from Earth to Saturn. Arrival is planned for 2034, when Dragonfly will enter Titan's atmosphere and descend to its primary landing site in a region called the Selk Crater Area. This region sits near Titan's equator, about 7 degrees north latitude, in terrain that shows interesting combinations of water ice and organic materials. The area likely experienced a meteor impact in the past that melted ice and mixed it with organics, creating conditions worth investigating for complex chemistry. Once on the surface, Dragonfly will spend time analyzing its landing site before making its first flight to a new location. The ability to move between sites, flying tens of kilometers to reach different terrain types, represents a revolutionary approach to exploring other worlds. Previous landers have been limited to studying whatever happened to be within their immediate vicinity, unable to move if the landing site proved less interesting than hoped. Dragonfly can simply fly somewhere else, visiting dunes, plains, possible lake shores, and various other features over the course of its mission. The nominal mission duration is planned for at least 2.7 Earth years, which represents about 1 month in Titan's seasonal calendar. During this time, Dragonfly will explore multiple sites, collecting data about atmospheric composition, surface chemistry, weather patterns, and the organic molecules present in different locations. The instruments include a mass spectrometer capable of identifying specific molecules in surface samples, cameras for navigation and scientific imaging, sensors for measuring atmospheric conditions, and even a seismometer for detecting any seismic activity or impacts. Power for the mission comes from a radioisotope thermoelectric generator, similar to those used by many deep space missions where solar panels provide insufficient energy. The generator converts heat from radioactive decay directly into electricity, providing steady power regardless of day or night or Titan's frequent hazy conditions. This power source will keep Dragonfly operating through Titan's long days and nights, each lasting about 15 Earth days, as the moon slowly rotates while tidally locked to Saturn. The flights themselves will be carefully planned and executed, with Dragonfly flying only during Titan's day when cameras can see the terrain clearly. Each flight might cover several kilometers to tens of kilometers, depending on the terrain and the destination, with the rotorcraft landing to recharge and analyze its new surroundings before the next flight. The progression of sites will build up understanding of how different environments on Titan vary in composition and chemistry, revealing gradients and patterns invisible from orbit. One of Dragonfly's primary science goals involves searching for chemical biosignatures, patterns in organic chemistry that might indicate biological processes or steps toward biology. The mission is not designed to detect life itself, and scientists do not expect to find living organisms in Titan's frigid methane lakes or on its frozen surface. Instead, Dragonfly will investigate how far organic chemistry has progressed in Titan's environment, looking for molecules or molecular patterns that represent advancement toward biological complexity. The findings will inform our understanding of prebiotic chemistry and the steps that might lead to life's origin. The mission will also study Titan's methane cycle in detail impossible from orbit, measuring evaporation rates, tracking weather patterns, and observing how the landscape responds to methane rainfall. By visiting the same sites at different times, or examining areas that have recently received rain, Dragonfly can observe the hydrocarbon cycle in action. Understanding this cycle helps clarify how Titan's surface evolves over time, and how materials are distributed across the Moon through atmospheric transport. Scientists hope Dragonfly might explore regions near the edges of lakes or seas, if the flight range permits, and if such areas lie within reach of the landing site. The interface between liquid and solid, between lake and shore, represents a particularly interesting environment where chemistry might differ from either the open lake or the dry interior. If accessible, these transitional zones could provide unique insights into how materials move between Titan's various reservoirs. The mission planning will balance scientific priorities against operational safety, keeping the rotorcraft within range of safe landing sites. Looking beyond Dragonfly, concepts for even more ambitious missions have been proposed, though none have been approved or funded yet. Ideas include submarines that could navigate beneath the surface of Kraken Mare or Ligeia Mare, studying the liquid environment directly and searching for currents, thermal variations, or dissolved materials. Other concepts involve balloons that could drift through Titan's atmosphere for months or years, studying clouds and weather from within. Sample return missions have been discussed, though the technical challenges and costs remain formidable for a target as distant as Saturn. Each mission to Titan adds layers to our understanding, from the distant observations of ground-based telescopes to Voyager's first glimpses, to Cassini's 13 years of detailed study, to Huygens' brief surface encounter. Dragonfly will add another layer when it arrives, providing perspectives that only surface mobility can offer. The progression resembles how we came to understand Earth itself, through exploration that moved from distant observation to visiting diverse locations and studying their particular characteristics. Titan deserves this patient, cumulative attention because it offers so much to discover. The Moon remains one of the most Earth-like worlds we know, in terms of active surface processes and complex chemistry. Yet, simultaneously, one of the most alien in its specifics of temperature and composition. Rivers flow there under an orange sky, but the rivers carry methane rather than water, and the sky is nitrogen-laced with organic haze. Seasons change, clouds form and dissipate, rain falls to feed the rivers, all in patterns familiar from Earth, but executed in substances utterly foreign. This combination of the familiar and the strange makes Titan endlessly fascinating to study. Beneath the surface, we can observe that global ocean of liquid water sits in darkness, a completely separate environment that may persist for billions of years without change. Whether that ocean harbors any form of life, even simple microbial life, remains unknown, and may remain unknown until future missions can sample it directly. For now, it exists as a possibility, a potential habitat, isolated from the surface world, by tens of kilometers of ice, and accessible only to our imagination and our instruments. The organic chemistry occurring at the surface and in the atmosphere continues regardless of our observation. The slow accumulation of complex molecules, proceeding at rates determined by Titan's cold and Saturn's distant sunlight. The lakes evaporate and refill with the seasons. The rivers carve their channels slightly deeper over centuries. The dunes shift grain by grain in the gentle winds. These processes will continue long after Dragonfly completes its mission, long after whatever missions might follow, independent of human interest, yet profoundly interesting to those who choose to observe. Titan orbits Saturn once every 15 Earth days, rotating synchronously so the same hemisphere always faces the giant planet. From Titan's surface, Saturn hangs motionless in the sky if you stand on the near side, or remains forever invisible if you stand on the far side. The moon's rotation locked by tidal forces established billions of years ago. The seasons march slowly through their long cycle, each one lasting over 7 Earth years. Summer in the north, gradually giving way to autumn, and eventually winter as Saturn continues its stately path around the distant sun. The universe has created here something remarkable, a world with weather and rivers and lakes and complex chemistry, all operating under conditions that seem impossibly cold and dark by Earth standards. The thick atmosphere that makes flight easy also creates the weather, enables the methane cycle, and hosts the photochemistry that builds organic molecules. The gravity that makes everything light also allows mountains of ice to stand tall without collapsing under their own weight. The distance from the sun that makes the world so cold also allows methane and ethane to exist as liquids, creating the cycles we observe. Our spacecraft have visited, observed, descended through that orange atmosphere and touched that frozen surface where methane rivers flow past ice rocks. The data they returned fills archives and continues to yield new insights as scientists analyze it with fresh questions and improved techniques. Future spacecraft will add to this record. Dragonfly flying across landscapes that Cassini could only glimpse through radar, visiting sites that Huygens saw only from above during its descent. The exploration continues because Titan rewards patient attention with discovery. The moon continues its ancient orbit, indifferent to observation, but open to understanding. Its methane cycle operating as it has for millions or billions of years. The rivers flow when conditions permit, carrying liquid downhill toward the waiting seas, following paths carved by previous flows, and cutting slightly deeper with each passage. The lakes accept the input, holding the methane until evaporation returns it to the air to complete the cycle again. This system will persist far into the future, the chemistry and the weather continuing in patterns we have only begun to understand. Tonight, as Earth turns and carries us through darkness toward morning, Titan orbits Saturn nearly 1.5 billion kilometers away, wrapped in its orange haze with methane rivers flowing beneath skies we have seen only through instruments. The distance makes no difference to Titan itself, which exists unchanged by our interest, following the same processes, whether watched or not. Our understanding grows with observation, but the world itself simply continues. A frozen laboratory of organic chemistry, where rivers that aren't water cut through landscapes that aren't quite like anywhere else.